Hi everybody, this is the next video in Unit 3. This is on Rolle's theorem and the mean value theorem. Here are the objectives below. Let's get started. I just want to do a quick review of the derivative and tangent line problem. Just reviewing just very briefly that the tangent to a curve is going to intersect this curve in one point. Right? So the slope of the tangent line is what we're talking about here, is the slope of the tangent line to a curve at that particular x point, that particular point. A secant line, of course, is going to intersect the curve in two places, and to find the slope of a secant line is pretty easy. Rise over run, change in y over change in x. But the slope of the tangent line is the limit. Remember, as these 2 points get closer and closer together until they reach that tangent, point of tangency. So I just wanted to show you this other diagram that we have here. This is the x-axis, right? These are y values here, here, and here. You can see that this is the secant line, right? This is the point where f of a is equal to f of b. And then there's some value c, right? That is a point of tangency on the tangent line, and you can see that the tangent line and the secant line are parallel. So if they're parallel, they have the same slope. So let's begin with Rolle's theorem. When we say that Rolle's theorem states, let f be a continuous function on a closed interval and a differentiable function on the open interval, a to b. So if I were writing this, I would include this as part of the if part. So f has to be continuous. So when would Rolle's not apply? Well, it would apply when the function is not continuous. And that would be where there is a jump, a hole, or an asymptote. Okay? Or it would apply, it would not be differentiable when there is a hole, when it's not continuous, so obviously you want to check for continuity first, or when it has a sharp corner or a cusp. So sharp corner and a cusp. All right? So that's when Rolle's would not apply. The other time that Rolle's would not apply is the if. If f of a does not equal f of b. Right, you know, those are the y coordinates at this interval, closed interval of a to b. So I'm going to write a point. Here's a point, maybe. Here's a point for f of a and f of b, where f of a and f of b are the same value. And then I'm going to have some kind of a function, something that would be kind of nice, maybe something like this, a little more interesting than straight across. All right, so what this says is that if it's continuous, which it is, if it's differentiable, which it is, and f of a equals f of b, which it does, so f of a and f of b are the same point, right there, then that says there's at least one number c in the open interval, such that the derivative at that point is equal to 0. And so we can see very clearly that there's a point right here where the derivative graph would be horizontal and thus have a 0 slope. And so in this particular case, there are two of them. So there could be more than one c value where that would be true. So determine whether Rolle's theorem can be applied to this function on the closed interval from 0 to 3. If it can be applied, find all values of c guaranteed by the theorem. All right, so let's determine if, first of all, is f of a equal to f of b. All right, so let's put that in here. So I do f of 0, and that's going to be 0. F of 3 is going to be negative 9 plus 9, which is 0. So check. Right? That part is true. When I look at the function f of x equals negative x squared plus 3x is a parabola. It is both continuous and differentiable so because it is a polynomial. So roles can be applied. So now the last thing is to find all c, so that we know that f prime of c, right? So that means take the derivative. So I have negative 2x plus 3 is my derivative. Put a c in here, right? Set that equal to 0. So I have negative 2c equals negative 3. So c is 3/2. And then I always check, is 3/2 in the interval? Yes, that's my value of c. Now once again, this whole thing is the answer because it asks for all those parts. The answer is not c equals 3/2. The answer is f of a equal to f of b, blah, 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 and all of that. All of this is the answer. So here's another graphic that I found illustrating what it would look like if you could apply Rolle's theorem. Okay, it says if f is a function that's continuous on a closed interval and differentiable on an open interval, and f of a equals f of b, then there is a number, c is an element of the interval, such that the derivative at c is 0. Okay, so I'm looking for maxes and mins. Agreed? All right, so here's my closed interval, right? There could be more than one place. So Rolle's theorem, when I go to apply, that last example I did had one answer, so it was probably something like this. Now, it's not telling me whether that was a max or a min, although I could have figured it out on the last one, because I know that it has to be a max, because it was a negative x squared, right? And here's another one that's negative. Now, what happens, this is f of a is equal to f of b, but it's a constant. So that means that f prime equals 0 everywhere. So these are all maxes and mins, local ones, right? We've seen that before. So now it is time for one of the most important theorems in calculus, and this is the mean value theorem, abbreviated MVT. But you're not allowed to abbreviate it until you know what the words mean. So just like if you don't know IVT is intermediate value theorem, this is the mean value theorem. And it says let f be a continuous function on the closed interval. This is sounding familiar. Doesn't it sound like Rolle's? And differentiable on the open interval AB. Then there is at least one number c in AB such that f prime of c equals f of b minus f of a over b minus a. That's starting to look familiar too. Notice that this looks like a slope formula, right? F of b minus f of a over b minus a, but no limit. So this is saying that the derivative, or the slope of the tangent line, is equal to the slope of the secant line. So let's look at a diagram that would illustrate this. So once again, I've got my xy axis, right? I have a and I have b. And then I have some f of a and f of b. And then I have some curve, right, on this closed interval, such that, oh, missed. That's close though. Do my little trick, make that bigger. Right, so I've got, and these are closed anyway. So once again, this is right here, f of a, and this is f of b. Now you notice it's different from Rolle's because f of a does not equal f of b. So this is different. Rolle's is a specific case of the MVP. I do that all the time, MVT. Okay, so what this is saying is that there is some c in here where the slope of the tangent line is equal to the slope of the secant line, and this is c. So this is our diagram illustrating, right, what this looks like. So the slope of the tangent line has to equal the slope of the secant line. And one last thing before we leave this screen is that you can rewrite this slightly differently. You can say multiply both sides by b minus a, and you get f prime of c times b minus a equals f of b minus f of a. Now all I did to get from here to here was multiply both sides by b minus a. Okay, so here we have the two theorems side by side. We have Rolle's theorem on the left, where we have a differentiable function and continuous function on an interval from a to b. We also have f of a equals f of b and a function, continuous and differentiable function between. For MVT, we have a and b, and then we also have f of a and f of b, which are not equal to each other, although they could be, right? And then we have down here, we have the then part of the MVT. We say that the instantaneous rate of change is equal to the average rate of change. But I want you to see that these are the same function. All right? So we know that if we are making if we're using the MVT, we're saying that the instantaneous rate of change is equal to the average rate of change. So remember that we find the average rate of change, the slope of the secant line, and that we know that there's somewhere else on the curve where the slope of the tangent line is parallel. And you can see here that there are a couple places where they are parallel. Well, you note that the slope is the slope of the secant line, or the average rate of change, not zero in this instance, right? Because it's positive. Okay, so that's what this is down here. Now, if you'll look here on Rolle's theorem, I'm going to change colors, but if I draw in the secant line, if f of a equals f of b, what is the slope of this line? Well, the slope of this line is 0, right? And for Rolle's theorem, we remember that f prime of c equals 0. Well, in this case, 0 is the average rate of change. So it's the same function. It's the same theorem, it's just that Rolle's is a little more specific than the MVT. So now it's time for an example. Determine whether the MVT can be applied to each function on the given interval. If so, find the values of c guaranteed by the theorem. Once again, this sounds an awful lot like Rolle's. Okay? So in order for the MVT to be applied, this function, given function, has to be continuous and differentiable. Is it? Well, it's a polynomial. It's quadratic. So yes, it is differentiable. Okay? So let's take the derivative. So f prime of x is equal to 2x. F prime of c is equal to 2c. And that's going to be equal to f of 1 minus f of negative 2 over 1 minus negative 2. F of 1 is 1. F of negative 2 is 4. And this is 1 minus a negative is 3. So negative 3 over 3 is negative 1. And so I'm going to set 2c equal to negative 1. And c is negative 1 half. I'm going to check to see if it's in the interval from negative 2 to 1, and it is. So this is a value of c. Now, what happens if you don't get a value for c, if for some reason it doesn't exist? Well, something went wrong, obviously. Either the function is not continuous or differentiable, or you made a mistake. And sometimes it's hard to tell, because some of these we did when we were finding critical values, it was hard to tell that there wasn't a critical value, and it's the same thing here. But those are the reasons why you wouldn't get an answer. But on this one we did, so on we go. Okay, so now I have one that I have 6 over x minus 3. This is not a polynomial. This is a rational function. It does have a closed interval. So I'm going to take the derivative, but first I'm going to rewrite it. So this is 6x to the negative 1 minus 3. I'm going to take the derivative, and that's going to be negative 6x to the negative 2. And then f prime of c would be negative 6 c to the negative 2. I'm going to find f of 2 minus f of 1 over 2 minus 1. F of 2 is 3 minus 3, which is 0, minus, and then f of 1 would be 6 minus 3, which is 3, over 1. So this is going to be negative 3. So I have negative 6 over c squared equals negative 3 over 1. Cross multiply, so I have negative 3 c squared equals negative 6. C squared is 2. So c is going to be plus or minus the square root of 2. All right, and then I'm going to check my interval. And I can see that negative square root of 2 is not in the interval. So square root of 2 is going to be my answer. Now, here's an interesting thing about this. Let's go back to the original problem. The original problem is this, right? So over the interval 1 to 2, because we got values for c, in this interval 1 to 2, this was continuous. So this is, again, back to that first video that we looked at, and that concept of open and closed interval, that any function can be continuous and differentiable over a certain interval. But if we change this interval, like say we wanted this interval to be from negative 1 to 2, then we would not find a c, because we know from the original function that x cannot be 0. We cannot divide by 0, and that's in this interval. But that value's not in this interval. There is a vertical asymptote for this rational function. So what was really important is if we'd worked this same exact problem, but we had done the interval from negative 1 to 2, we would not have found the values for c. So changing that interval is very important. Realizing what the problem looks like and what the interval looks like helps us then to determine continuity and differentiability. So there's a lot in here. You may want to watch it again. Are you noticing how the vocabulary is just building, building, building? So if you don't understand closed and open interval, this is a little more painful. So be sure that you understand the basics, and then be prepared to work a lot of these MVT and rules problems. We're working on the verbal component as well, being able to explain our answers. So I will see you in class.